Hello, good day. Today we are going to discuss the stresses beneath the corner of a rectangular foundation in our subject Foundation Engineering. And we have now this simple illustration for the vertical stress under the corner of a rectangular foundation in which we are considering an infinitely small unit area here of size dB with this differential width and this differential length. And the pressure acting on this small area here, shaded area, may be replaced by a concentrated load, this differential Q. Okay, because this is a differential area, so we are also considering a differential load, capital Q, applied now to the center of the area. So by formula, the vertical stress sigma z is just equal now to this formula here. Small q, the unit pressure, over the 4 pi times this here, this quantity here, inside. Okay, so if you reduce this vertical stress formula, it is simply equal now to this q over z times this I, which is our influence factor, this dimensionless factor, which is the influence of a surcharge, since we are considering here uniform pressure, this q. Okay, so our m is just simply equal now to the ratio of your b over the depth z, and your n is just the ratio of your length here over the depth z. So as you can observe here, we have this point P here, in which we are going to calculate the sigma z. And if we extend a line through this point in our width of this rectangular foundation, so each angle is just simply equal now to this alpha 1 with respect now to this vertical axis. So as for this differential area, in which if we extend a line from point P to this point of this differential area, in which we are considering this differential with dp, is just having this angle of alpha from or with respect now to this vertical axis. And so for the angle between this point of this differential with b, it is we denote this one as our differential angle alpha. So considering also the length of this rectangular foundation, so from this point p extending to this point, so we denote this one with angle beta 1. And we have now this differential area considering now the differential length from this point extending to the point P, and from this point also extending to the point P. So this angle would be equal now to beta, and its angle here, considering this differential length, is just equal now to the differential angle beta. Okay, so we have here chart or the influence diagram if we are going to encounter some problems with regards now to the calculation of the vertical stress considering the rectangular foundation, in which in this figure 2 we have a chart for computing the vertical stress below a corner of a rectangular foundation by Steinbrenner of 1934. So we have now this vertical axis of z over b, and then we have now this value of the x, which is the values of our influence factor I. And from this one, we have the value of our curved lines here, which is referring now to the ratio of our length over the width. And if you are going now to determine the influence factor I, having this L over B and having also this Z over B, so we can actually get now this value of I if we are using this step, this chart rather. So we have here the length, the definite length. We have this width, then with a given uniform pressure of small q, and with this load acting at a depth z, from the Earth's surface. So same also for this figure 3, which is a graph also for determining the I value, in which we can also use this one for uniformly loaded rectangular area by FAD of 1948. So the vertical axis now is referring now to the values of our influence factor I, and then we just have to get now the value of our m, which is just the ratio of your width b over the z. And then afterwards, you also get now the value of your n, which is equal now to the ratio of your length over the z. So after getting this one, we can actually have this value of our influence factor I. Okay. So we have actually two cases no for load no when our point is located inside the rectangular foundation or when the point is located outside. So for the case 1, we have a simple drawing here referring to figure 4 when the point O is within the rectangle. Okay, so for this purpose, no, we divide the rectangle ABCD into 4 smaller rectangles marked by this 1, 2, 3, and 4. And by drawing no lines through this point O here. And for each of these rectangles, compute the ratios no, of your Z over the B. And then the influence value no, may be obtained no, from the given chart as shown in the previous slide, or we can calculate using the formula given, referring now to the m and n values no. And for the case number 2, we have the point is outside the rectangle or rectangular foundation ABCD. So we have to consider now this no, extension of this point A to A1 and B to B1, also for this A to D2 and for D to D1. So for our formula for this, we have now this area ABCD is just equal now to OB1, then we have now this C and D1. So actually, we are referring now to this area actually. So this is OB1CD1. So minus OB1, this OB1, and then this B and this D2. So this area is referring again to this one. Okay. So minus this one. Minus again by OD1, DE1. So we refer now to this area. Okay. And lastly, we have now this plus O A1 A D2. So this would be now our last rectangle here. Okay. So to calculate now the vertical stress sigma Z, it's just simply equal now to the Q, the uniform pressure Q times the influence factor, no? Where in this case we have this influence factor 1 minus I2 minus I3 plus this I4 as shown in this illustration. No? So actually this sign no, of this influence factor is referring now to also this consideration no, in calculating the area of our rectangular foundation ABCD. Okay, so we have here a simple problem no to use the formulas or even the given chart no if we really wanted to, but as of this time we are just more on the formula, how to apply the formula in calculating the vertical stress. Okay, so we have here the ABCD, which is a rough foundation of a multi-story building in figure 1 as shown, and wherein our EB is given this side, which is 65.6 feet, and our BC here, which is 39.6 feet, and the uniformly distributed load Q, small q over the rough, is 7,310 pound per square feet. And we are going to determine the vertical stress sigma Z at a depth 19.7 no, which is our Z below this point O, wherein our AE1, this AE1 is given with this 13.12 feet value, and this A1 2.0, which is equal now to 19.68 feet. Okay, so actually this is now referring to case number 2 no, when the point O is outside the rectangular foundation no, which is our ABCD. So we have here our solution. No? I prepare a table for this, and so that we can calculate it, no, more briefly. And then this is just the formula, no, from our previous slides, in which we are going to calculate, no, the value of our vertical stress sigma z using the m and n values. And also, after getting this one, the influence factor, so our vertical stress is just simply, no, the uniform pressure Q times the influence factor. Where in this case we have actually four influence factor, no, referring now to these four rectangles as discussed, no, in our previous slide. Okay, so given the problem is actually we have now this side AB, no, which is equal now to 65.6. Okay, this is 65.6 feet. Okay, so another given is the side BC actually. So this side BC is just equal now to 39.6 feet. Okay, and the other given side is we have this A1. This is also given. Okay, so this is equal now to 13.12 feet, and we also have now this A1 to point O, which is equal now to 19.68. Okay, so we are going to fill up here, no, the values of our length and also with our corresponding width. So after getting this one, so we are going to get also the ratio of our length over the width, and also for the depth z over the b, just in case if you are going to use the chart, no, in our previous slides, to calculate now the value of our influence factor I. But in our example, we are just concentrating, no, on this formula, using this formula, and then we get the m and n value here, and then afterwards we get now the value of our influence factor I, and subsequently we get now the value of our vertical stress sigma z. Okay, so first, for O B1 C D1, we actually have now this length, no, for this O B1 C D1. Okay, so our length is just simply equal now to this 19.68 plus this 65.6, which is equal now to 85.28 feet. Okay, okay, so next, for our next rectangle, which is O B1 B D2, so they have the same, no, they have the same length also, which is 85.28. How about for this third rectangle, which is O D1 D and this E1? So this side is 19.68, no, but this side is 13.12 plus 39.6, so this would be now our length, which is 52.72 feet. Okay, and we have also now for this rectangle O E1 A D2, so we have now this side which is 13.12 and this side is 19.68, so this would be now our length, 19.68, okay, feet. So we are done with the length, no, and we are just going to get now the width of this four rectangles. So for the width here, it is just equal now to 52.72 feet. For the second rectangle is we have this 13.12 feet. For this third rectangle, we have now this 19.68 feet. And for this fourth rectangle here, we have this 13.12 feet. No? So after this one, we are going to get now the value of our ratio of L over B and this Z over B, just in case, no, if we opt to use the chart, no, to get the influence factor I. But for the sake of discussion, I will just get now this value of L over B and this Z over B for the four rectangles. Okay, so we have here 1.6 62. Here is we have 6.50. Then we have here 2.68. Also here we have 1.50. And for this z over b, we have this 0.37 here. And also here we have this 1.50. And here we have this 1.0. And here we have now this 1.50. And for our m, which is just equal now to the ratio, no, of our b over the depth z, which is 19.7. So if you are going to calculate now this 52.72 feet divided by 19.7, so our m will be 2.67. Okay, so as for this next three rectangles, no, we have now this 0.67 here, and also here we have 1.0. Also here we have 0.67. For our n, which is just the ratio of your length, no, this length over the depth z, so we get now the value of 4.33 here. For the second rectangle, we have same, no, 4.33, since they have the same length. And also for the third rectangle is 2.67, and we have now this last rectangle, which is 1.00. So now we are only after, no, to this influence factor I. Since after we get this one, so we just simply multiply this with our uniform pressure Q, and we get the value of our vertical stress, actually sigma z. Okay, so we have now this formula. Okay, so for our influence factor I, we actually have now this I equal now to 1 over 4 pi times, we have now this 2mn times this m squared plus this n squared plus 1 raised now to the 1 half over this m squared plus this n squared plus this m squared n squared plus this 1. Okay, and then we are going to multiply this with this m squared plus n squared plus 2 all over this m squared plus n squared plus this 1. Okay, and then we are going to have this plus the inverse tangent of this quantity here. Okay, so we have here 2mn times this m squared plus n squared plus 1 raised now to the power of 1 half all over this m squared plus n squared minus m squared n squared plus this 1. Okay, so bracket. Okay, so we calculate now this first this rectangle O, B1, C, D1, no, using this first influence factor, no. So considering now the first rectangle, no, this O, B1, C, D1. So we have now this formula for our influence factor. So 1 over 4 pi times. So we have now this value of our 2mn. So we have this 2m and n. So 2 times 2.67 and n is 4.33, and then we multiply this with 2.67 squared plus this n squared, which is 4.33 squared plus 1 raised now to the 1 half. Okay, all over this m squared, which is 2.67 plus 4.33 squared plus 2.67 squared, 4.33 squared plus this 1. Okay, and then we are going to multiply this with this m squared, which is 2.67 squared plus 4.33 squared plus 2 all over 2.67 squared plus this 4.33 squared. Okay, plus 1. So we have here, and then plus this inverse tangent, no, of this quantity here. Okay, so proceeding with our calculation, no? So we have here, so for inverse tangent, so we have here plus our inverse tangent here, negative 1 of this one, no? So 2mn 2 times m is 2.67 and then 4.33, and then we have now this quantity here. So m squared 2.67 squared plus this 4.33 squared plus this 1 raised now to the 1 half, then all over this m squared. So 2.67 squared plus this 4.33 squared minus 2.67 squared times this 4.33 squared plus 1. Okay, so we have now this calculation, no? And as we can observe, no, from this calculation, that our third value here, no, is having a negative sign. Take note that this one is in region, but if ever that this will be having a negative sign, so we need to add, no, with this pi region, so that this could be equal now to a positive value. Okay, so for our I is just equal now to, for our first here, the result of this one will be equal now to 0.1 over 4 pi times first result is 0.746709, and then multiplied by 1.037205, and then this is quantity here, and then we have now this inverse tangent of the result of that one is actually negative, no, if you can observe, negative 1 0.1262. Okay, and proceeding, we have now this value of our I, which is 1 over 4 pi times the this one, which is just equal now to 0.7745. Okay, plus, and the result of this one, no, inverse tangent of this is just equal now to negative 0.8431. Okay, so since this is negative, so we need to add this one, no, with a pi. So this would become equal now to 1 over 4 pi times 0.7745 plus this pi plus this negative, no, 0.8431. Okay, so our I is then equal now to, we are going to simplify this one. This would be equal to 0.245. Okay, so this would be now for our first influence factor, no, considering this rectangle O B1C D1. So actually we can input it here. So this would be equal now to 0.245. Okay, so for our next rectangles, actually for this OB1BD2 until this OA1AD2, actually their third term, no, this term, this inverse tangent of this one is already have a positive value. So you don't need to add, no, this pi with regards now to the result of this arctangent. No need to add this pi region if the result of your arctangent here is already positive. So you can proceed now directly, no, without adding this pi region. So using the same calculation and formula for this, we can actually have these influence factors of our second, third, and fourth rectangles as follows. Here it is equal now to 0.167, and for this third rectangle we have now this 0.203, and for this fourth we have here this 0.145 here. Okay, so proceeding, no, after getting all these influence factors, so we can actually get now the value of our what's called the vertical stress, no. So after this one, we have this value of our vertical stress. Okay, okay, so our sigma z. So our sigma z is just simply equal to this small q times our influence factor. Okay, where in this case this would be equal now to sigma z is equal now to q times this influence factor 1 minus influence factor 2 minus influence factor 3 plus our influence factor 4. Okay, as you can see in this formula. So our sigma z is therefore equal to, so this would be equal now to our q is given, which is 7310 times our I1 is 0.245 minus I2, which is 0.167 minus 0.203 plus our I4, which is 0.145. So our sigma z is just simply equal now to 145.27 pound per square feet. Okay, so this would be now our vertical stress actually for the said problem, which is 145.27 pound per square feet. So this would be it, no, for this problem. And if you intend, no, to use this ratio of L over B and this Z over B using the chart, so you can do so and you can compare, no, the answer of our vertical stress sigma Z there. So this is now the application of this formula in calculating the vertical stress, no, for a rectangular foundation. Okay, so proceeding for our next slide, we have now this simple problem here. Okay, a rectangular raft of size 30 by 12 meters founded on the ground surface is subjected to a uniform pressure of 150 kilopascal. Assume the center of the area as the origin of coordinates 0, 0 and corners with coordinates 6 and 15. So calculate the induced stress at a depth of 20 meters, which is our Z, by the exact method at location 0 and 0 coordinates. So this is now, no, our illustration for this, which this is case number 1, no, in which the point is inside the rectangular foundation. So we have now this four small rectangle, 1, 2, 3, and 4, and we have now this width here and this length of such rectangle, no. Okay, so proceeding with this problem number 2, our approach this is this. We have now this table, no, and then we are going now to get also now the length and the width, and we have also the m and n, and correspondingly we can get now the value of our influence factor I. So if you opt to use again, no, this ratio of L over B and this Z over B, actually we can do it, so, no, if you really wanted to, but for the case of discussion, no, in this problem, so we try to get also these ratios of L over B and Z over B. Okay, so here we have now this four rectangle, no, A, E, O, and this G. The second one is this E, B, H, O. The third is this O, this H, C, and this F. And the fourth rectangle is the G, O, F, and your D. As you can observe, they are all symmetrical, no. They have the same width and they have also the same length, no. So filling this up, no, with values of our length, no, and with our width, we have now this for the first rectangle. We have this 15 meters, no, for our length. This side 15, and also for the other rectangles 15. Okay, and for each width, we have now this width now of this 6 meters. Okay, 6 meters. We have here 6 meters again. and 6. So for this ratio, actually, if you hope now to use the chart or this or that influence diagram, so it's just equal now to 1.62 here, and this is 6.5, and this is 2.68. Okay, so I'm sorry, no. So this is actually the same, no, for all the ratio, no, since we have the same length, no, and the same width. So just try to erase this one. This L over B is just simply equal now to 2.5. Okay, so we have also here 2.5. And for our Z over B, actually they have the same also ratio, no, of 3.34 here. Okay, so for our M is just simply equal now to the B over the Z, which is equal to 0.3 all throughout, no, for these four rectangles. Okay, also for the N, which is the ratio of our length over the Z, which is just equal na 2.75 for all rectangles here. Here 0.75. So we are just after, no, of this influence factor I using this formula and multiplying the influence factor, no, with this uniform pressure Q, we can get the vertical stress. So take note, the signs here are all positive, no, since they are all, no, the point O is just inside the rectangular foundation, so that's why it is plus here. I sub 1 plus I sub 2 plus I sub 3 and plus this I sub 4, no, and we multiply this one with our small q, we get now the vertical stress. Okay, so using the same, no, the same formula for our influence factor actually, so we can get now the value of this four rectangles, their respective influence factor, no, for the first rectangle, for our I, for this E, and this JO, this is just equal now to 0.071. Okay, so this is also the same now for the influence factor for the other rectangles here, for the E, B, H, O, which is also equal now to our O, H, C, F, and which is also equal now to the influence factor of our last rectangle, okay, F and D. So therefore, our sigma Z is just equal now to Q times this I. Okay, so Q times this I sub 1 plus this I sub 2 plus I sub 3 and this I sub 4. Okay, so we can actually fill this one up now with the value of our influence factor of 0.071. Same also here for the second, third, and fourth rectangles. Okay, 0.071 and 0.071. Okay, so therefore our value of our vertical stress, no, substituting this one, this is just equal now to sigma g is equal now to our q is 150 times our 0.071 times 4. Okay, so we actually get now the value of our vertical stress, which is just equal now to 42.58. Okay, kilo Pascal. So this would be now the vertical stress, no, for this problem number 2. And I think this is a simple, no, illustration and discussion on how to use this formula actually in calculating the vertical stress, no. So I think that would be it, no, for this day regarding the stresses beneath the corner of a rectangular foundation. And I hope you get this one up, this formula, and for further discussions and for further topics, no, we can still use this formula in calculating the vertical stress beneath the corner of a rectangular foundation. So thank you very much for listening and watching, and these are my references, no, with regards now to our subject, foundation engineering. And once again, please don't forget to like, no, to unsubscribe and even share, no, for more updated videos regarding our subject. And thank you very much again for watching and listening. God bless us all.